Catherine obviously has a phenomenal amount of experience in volcanology in the Canadian context, graduating from UBC many years ago, we'll say in the mid-1980s, and has had a fantastic career with the GSC, retiring a little over 10 years ago and diversifying off into the geothermal consulting and business side of volcanology. And obviously with her work in BC and other places collaboratively, she's built quite a reputation for modern volcanology, especially in the Canadian context and related to melt interaction with ice and water. So thanks again for doing that today. Catherine, I'm just going to turn it over to you.
Oh, thanks. Thanks so much, David. And it's great. I see old faces and new faces, really. And I'm sorry, I've been getting the messages for these, but I am still working full time, as David has said. I just was recently appointed the CEO of an Alberta-based geothermal company, and it's been busy. So my apologies that I haven't caught any of these webinars up until now, but I think it's a fantastic initiative. And also, and I reached out to Dave, and this is the 40th anniversary of Mount St. Helens, and it was certainly important for my career. And I really, I wanted to share some of that with, friends and colleagues, because it was certainly an incredibly important event for volcanology. So I'm just going to share my screen, and I think.
Yeah, I shared, yeah.
Okay. Can you see the presentation?
Yeah.
Perfect. Okay, let's go to the beginning. I've got multiple screens here, so if I get a little, it's because I'm looking at various things. So this is the 40th anniversary, and the first thing I can say that part of Mount St. Helens for me was not just being an eyewitness, but having the opportunity to work with people, and one being Jim Moore. And I don't know if any of you actually know Jim, but I'm going to give you a little bit of background for Jim. So Jim this year is the GSA's Penrose medalist, and as I say, there was a little bit of confusion on my part. I actually didn't realize there were two Penrose medals. One is given by the Society of Economic Geologists and one by the GSA. And when I went to the SEG website, I didn't see Jim's name, so I thought, oh no, like what? As one of the nominators, we had been informed that he had received the award. So anyway, it was my confusion. It's actually the GSA Penrose Medal. And what you see is really the citation in terms of what he did. And what I'm going to focus on are the high velocity base surges and the 1980 Mount St. Helens work that he did. So Mount St. Helens, May 18th, 1980, 40 years ago. That was really, it went from that to that. And given that that is in the conterminous United States, the impact of that eruption in terms of essentially people was, of course, incredible. But scientifically, it was almost even more important, because its proximity to populations, its proximity to scientific research institutes meant that it was the focus. So those of you who were around at that time might remember, I mean, it's not that long ago, I was a third-year undergraduate student at the time, and it was the talk of every department across North America and probably into Europe, what was going to happen at Mount St. Helens. So as a student, my husband and I, we made our way down to Mount St. Helens, kind of the first opportunity we had, which happened to be a the May 24th long weekend, but it turned out that was actually included May the 18th. And we were not the only eyewitnesses. There were a number of them. And all the reports of the eyewitnesses are chronicled in this Richard Waite's book, A Path of Destruction. And there you can see. So what Richard has done is he's put together all of these observations, because one of the important things about Mount St. Helens, not just from the perspective of uh, the science, it was the most observed, the most photographed eruption. And there were many people that provided a perspective from different aspects of the volcano from all the way around it, northeast, south, and west. So I was so lucky in that lucky to be alive. I guess that's number one, but also to have had the opportunity to, to work with some of the very important volcanological figures of the day, one being Don Peterson and the other being Jim Moore, and others. But these two gentlemen had the most influence on my work at Mount St. Helens, as well as my work going forward. Unfortunately, Don passed away not too many years after he retired, and is no longer with us. But Jim is hale, he's coming up to 90. And in fact, this presentation was put together for a small symposium honoring his 85th birthday, so a few years ago. How I look upon Jim is really the father of pyroclastic surges or base surges, and that's what we're going to. So here we are actually on Surtsey. This is the envy of many of my Icelandic colleagues, because it's very hard to get at Surtsey. But Jim was there when the initial eruptions were happening, and he has made a point of going back basically every year for the first decade, and then every decade thereafter. So I've had a great time. Whoops. So the important thing from a scientific viewpoint was really understanding what happened at this event. And literally there are thousands of papers that have been authored, and many of them have been contributed by Jim. And really most of the work focuses on how did we get from this, Plinian eruption column to this crater that had, a significant amount of material moved on it. So the things that are important for everyone here to remember is we are talking about 1980. It doesn't, for me, it doesn't seem very long ago, but there were quite a few things that were really not understood in 1980. And that was, number one, the landslides, these sector collapses, as well as the lateral blast. And what Jim did is he basically took what had happened from all the eyewitnesses' accounts, and he put together essentially what had happened in that March to July timeframe. Now, important for him were our photographs. So you can see the schematic version here and what he did. So with all of the photographic record, he put on the topography of the volcano and then sketched in what was happening at the volcano. And the importance of our photographs is we were, as you can see from the angle here, we were east of the volcano and slightly south. And what that meant is that our view was not obliterated by the surge cloud until later in the eruption. And I'll show you those photographs. So everybody who was to the north of us didn't see some critical elements, and those critical elements were actually this eruption plume, failure of this block, as well as the failure of the third block here. What's interesting is, I mean, Mount St. Helens was known that it was a very active volcano. It had last erupted in 1853, you know, but as people, as humans, we don't have a very long time frame in terms of our memories. And so by the time 1980 rolled around, the Spirit Lake was tourist haven. You can see all the boats and people out here. And of course, it was a phenomenally beautiful place with this gorgeous stratovolcano. But it had been predicted that it would erupt again before the end of the century. Back in 1975 papers, or 79 papers. So the activity started in March. Soon we had this gaping hole with steam as basically a graben opened up on the surface. You can see the eruption of the 1980s was here at Goat Rocks. The important thing, though, was we had the opening of that summit graben, but we grew this bulge, and that bulge was growing at its maximum rate of over 2 meters per day. And as these events started to unfold, it really was the talk of geological departments around the world. So in this is our first photograph. This photo was taken the evening of May 17th. And what you can see here profiled is that bulge. So by the evening of May 17th, though, it was very quiet. In fact, the bulge had been growing, the bulge was continuing to grow, but it was relatively quiet. You can see there's no steam coming from the summit, and it looks very tranquil. So we headed south on May the 16th for the weekend, and where we entered was here, for the town of Randall. We came down here. Here's Mount St. Helens, and this is where we were when we were viewing the eruption. And we had 2 dogs with us, and that's another story. Most of the observers were basically in an arc, and there were a few people to the south, as well as actually on the nearby. There was a group of climbers on Mount Adams, as well as climbers on Mount St. Helens. So there it was, the evening of May 17th. We were then having breakfast. We saw the eruption from its initial moments, but this is the first photograph. And you can see these 2 eruptions, the flank explosion, the summit explosion. You can see the landslide, you can see the second landslide, and the third landslide, which actually took off most of the mass, has not yet failed. So from the work of Jim and others, this photograph, and that was, a lot of it was based actually on the satellite imagery. This photo was 25 seconds into the eruption. We then started the camera rolling pretty quickly and took this couple of pictures. We are now going to run forward. We're now running forward, so the perspective is changing just a little bit. But what you see here, we're now 39 seconds into the eruption. And what's important here is that here's the slide block. And that was the slide block that most of which entered Spirit Lake first. It is now being overtaken by these explosions. This pyroclastic density current, pyroclastic surge that is now enveloping that. The middle landslide has basically dropped into the back of the first landslide, and we're also starting to see the arching and motion of this upper explosion onto the flank as opposed to vertical. So now we've we have run forward. We're at 55 seconds into the eruption. And what you see here is those two explosion clouds have coalesced. And we're starting to see the cloud come over that eastern flank towards us. We're now 70 seconds into the eruption. The other critical thing about this photograph is you see this very sharp front. So this is our density current. This is the pyroclastic flow that was shooting out to the north and did most of the devastation. But what's kind of not known is that that density current, it spilled over 360 degrees, both to the east and to the west, as well as to the south. As it gained momentum, it actually crested over the peak. And we also had, remember, the failure of this third landslide block. We're now 80 seconds into the eruption. That the northward view is out of our plane of view. The third landslide hasn't erupted yet, but you can see actually this is the beginning of the Plinian eruption, that little shoot going off. But now clearly this is starting to cascade down the eastern flanks before us. We're now 120 seconds, and for us now, the volcano is completely obliterated. And you can also see the berm in front of us. We are now running. We have running for our lives, jumping into our car, heading as quickly as we can to the south. This is the photo that I've taken from the car window, looking back at the surge cloud basically chasing us down the highway. Here again is, there's that view from the evening. These are the landslide blocks that failed that day. And what is important here is that this lower pink, so this is the 1853 eruption of Goat Rocks. This is an older, the light pink here is also from an older summit eruption. But this red zone here was called the cryptodome. And crypto simply being hidden because it in fact was intruding into the mountain, and that was what was creating that bulge. There was a lot of discussion about what was happening. But from the observation and a look at the earthquake record, this landslide block, the biggest, actually the biggest of the blocks, that block, and that was work that was done at the University of Seattle, looking at the seismology group there, and that was what created the landslide. It was not the earthquake that created or started the eruption. So, and think about, and this is actually where some of the eyewitness reports came in, because there was certainly we felt no earthquake prior to that eruption starting. I'm not sure why we looked up. In any case, the eruption did not start by an earthquake, but the impact of this landslide block into Spirit Lake created a significant earthquake. So here's the second landslide block. You can just see the top of, and again, that's the schematic of what that looked like. And here's the point. So we're about to lose that third landslide within the next 5 minutes. That the third landslide goes down. There it is, cascading down with that flow front. And we're now 80 seconds. So this is 2 minutes after the start. This photo And it's not clear when that third landslide, but it occurred somewhere between 2 to 3 minutes. And again, from the car window. So we were moving as quickly as we could. This photo, we have now sped down the road, taking the photos out of the car. And what we're seeing here is we have now managed to escape the blast, and we now have a view. So what has happened is the surge has spread out. It has, you can see that, so the residual cloud. What is important is that we've now developed that Plinian eruption column. And that Plinian, the upward motion of the column has basically sucked the air, sucked the ash that was in this vicinity upwards, clear view of the southern flank. And the earthquake, or sorry, the third landslide has now decapitated the mountain, and it's gone in this picture. So this is another, and about 15 minutes. And in 15 minutes, the column was 25 kilometers in height. And you can see the very conspicuous mushroom cloud that was forming and heading off mostly to the east. So what about the surge? What about what was called at the time the directed blast? And so this kind of photographic evidence was really one of the, the first chronologies, other than Jim's blast, these phreatomagmatic events in process. And this one I've just added that that second slide showing you the 25 kilometer high, 15 minutes, and then the third landslide block that has now failed. So this is the devastation that occurred. It's actually 32 kilometers from the center out here. This is where we took those pictures, and you'll see that we were not in the devastated zone. Thank goodness. I mean, we wouldn't have survived, but we were still at a point where the cloud had enveloped us and passed over us. This is just a view looking north to Mount Rainier. And in that blast, 600 square kilometers of alpine was basically destroyed. And that is Spirit Lake. And in the foreground here are the landslide deposits. And what you see are trees floating on the surface. Where the trees were left standing and had not been harvested. So some of the devastation that you see, for example, in the back here, is not trees that were removed by the blast, but in fact it was an area that was logged prior to the blast. But in areas where there was still standing timber, this is what it looked like somebody had taken a comb through it. Now, at that time, again, hearkening back to the two important phenomena that were observed at Mount St. Helens was the landslide, which was the largest observed landslide and remains the largest observed landslide, and the pyroclastic surge. At that time, there was a great debate about whether these kinds of events were laminar or turbulent flow. And so what I brought to the picture is, an observation of what these events took place, but also just, like this was turbulent. What I saw was this roiling flow front that enveloped the trees. I could see the trees basically disappearing underneath of that flow front. There was no doubt in my mind. So remember, I'm a third-year student. I'm just taking my volcanology courses. I'm just learning about laminar and turbulent flow, and the debate that was raging at that time. And I'm going, this is turbulent. There's no doubt about it. But of course, this turbulence had already been noted by a number of workers. And so there's lots of synonyms for pyroclastic surge, ground surge, blast, et cetera, et cetera. Surtsey played a big role in this because it was also phreatomagmatic, and looking at the deposits of Surtsey were important in terms of understanding these kinds of phreatomagmatic events. The definition remains as a destructive, dilute, fast-moving density current. And in fact, many modern researchers referred them as density currents. So that helps actually increase the understanding that these are dilute, fast-moving currents. Instead of being water and particles, they are in fact particles and air, or steam in most cases. So this, though, the whole thing about base surge basically starts with Jim back in 1965, and he witnessed the eruptions of Taal volcano, and basically documented these base surges, as they were called then, these explosions that were phreatomagmatic, that spread out in more or less 360 degrees around the volcano, and were incredibly destructive, but left a very ephemeral, thin deposit in most cases. So again, this is all stuff that I was learning at in class, and my classroom got to be transformed into Mount St. Helens. And so because of being an eyewitness, I was allowed to go back with a number of the researchers. Here I am with Pete Rowley and Dan McLeod, and there happened to be an explosion while we were on the ground. And you can't tell in this photo, but I'm actually running faster than both of them back to the helicopter. And then here I am taking samples of the deposit. And what I was trying to prove there was the orientation of the class, that the class had been deposited by a turbulent flow. So that went, that was kind of what I was doing, but at the same time I was corresponding with a number of the USGS colleagues, including Jim, and it was really Jim's, Jim was the one that said, this is a pyroclastic surge, this is phreatomagmatic, and laid the foundations of what myself and others had observed. In 2013, I was asked to contribute to the Encyclopedia of Natural Hazards, and so what I tried to capture in that work, now a few years ago, is the history of this. Jim's early work, how he pulled in the observations from the atomic blast, basically those observations, and his observations basically on Taal, but it was first documented actually in the Azores in 1957. So, all of this work is old work that has great beginnings. And this is just a picture of the Trinity Atomic Web photo, and you can very clearly see the base surge. So it was the problem that happened kind of after this is that there was a muddling, and because observers were now seeing laminated deposits that were associated with column collapse of typical Plinian column collapses of typical pyroclastic flows, it ended up being a very, like, what was this? Was this the result of an explosion, or was this the result of a deposition as a suite of products, of facies of a pyroclastic flow. So in the literature, the problem became that everybody was calling, if they saw something that was laminated, it became a surge. And so I was taking the viewpoint of somebody who had to deal with hazard and risk and emergency preparedness. And what I recognized was the importance of these thin ephemeral deposits, and those thin ephemeral deposits, their incredible impact. So despite them being thin, despite them being very ephemeral, so in when we're looking in old deposits, we don't necessarily even see them. And so they are underestimated when we're doing hazard assessment at volcanoes. So that was really what, kind of what I was trying to do, was to put this together as its importance from the perspective of emergency managers and people who were doing hazard mapping and risk assessments. Don't underestimate these thin ephemeral deposits. Make sure that you are looking closely at the deposit and ruling out whether or not it's phreatomagmatic. And there are a number of specific particle morphologies. Particles tend to be broken, they're quenched, fractured, they're not pumiceous or only slightly pumiceous. So there's a number of things that can be used to identify whether or not you're looking at a surge deposit or whether or not you're looking at a pyroclastic flow deposit. So for the 25th anniversary, and I can't actually believe it's 25 year, it was 25, I put together this book for popular press, I would say, and putting the photos and whatnot out there. And of course, I do lots of I do lots of speaking engagements to students, to colleagues and whatnot like this. And what I have to and I want to emphasize is that, we do have volcanoes. And it's, there's lots of them, particularly here in British Columbia. We've actually even had seismic swarms around the Nazca volcano. That was, now a couple of decades ago, but don't want to date anybody. And then, of course, the fumaroles that were discovered at Mount Meager. So, we do have lots of volcanoes here, and that's why I think we have spawned such a strong volcanological community, because, we have students who are able to work on these Canadian-based volcanoes, and these are students from all across the country. So, that's kind of neat, sort of pushing that, that piece. And I was able to work with Jim. So after Mount St. Helens, he came and he wanted to visit our subglacial, our phreatomagmatic volcanoes. So we did 2 trips up to the Tuya Buttes field, as well as to Wells Gray. And I know in the citation, and I want to put in the citation for Jim, it said that he was the one that had put together the morphology of tuyas, and that's actually not true. That belongs to Bill Matthews and some Icelandic colleagues. The difference between what Bill did is he published in English, and so his descriptions of the Mount Tuya or Tuya Butte were sort of picked up by the international community, but it certainly had been recognized in Iceland that these were volcanoes that were related to subglacial eruptions. But it was great to be able to get out in the field with Jim, and here we are up in the Tuya Teslin area. And I love this photo with the giant pillow. So, I just want to emphasize that we have fabulous volcanoes here in in Canada, Mount St. Helens is right next door, so it also is a great laboratory, but I don't want people to run away to Mount St. Helens and forget about our volcanoes right here, because we know so little about many of them. But certainly the research over the last decades have helped us in terms of our increased understanding, and certainly seeing something like an eruption of Mount St. Helens has helped volcanologists everywhere in their volcanological studies really understand these kinds of eruptions from snow-capped temperate volcanoes in Canada and around the world. So thank you.
I finally found how to unmute myself here. So thanks a lot, Catherine, for that trip down memory lane, really. I didn't realize how close you were, and I wasn't aware of your book, just some of the papers, obviously, on this. So thanks again. We have quite a few people on the line. As anybody wants to ask a question, so far I have no questions, Catherine.
I can't believe that. John Sticks, I haven't seen you for ages. How are you?
I am good. Great to see you, Kathy. It was a great presentation. And I actually have a question for you.
Good.
Okay. When you were watching the blast come out, could you tell that it was maybe not an average pyroclastic flow, that it was more than a pyroclastic flow, that it was, you said it was violent, but could you appreciate the true violence of it at the time, or not really?
Not from a scientific perspective. It was, a fear. I mean, because you can see by the sequence, those pictures were taken pretty fast. And initially, when we first saw it, what we saw was the summit explosion happened first. And we could see that there was something happening in the slope. And so at first, my ex is also, he's a scientist, he's an astronomer. And, so we both have sort of scientific minds and thinking, wow, like that's really weird. What is going on? So, but by the time we grabbed the cameras, we were 25 seconds into it. And at first it was just like, oh my God, like what is happening? Like, this is amazing. And then fear began to take over. Like as soon as it started cascading down that east flank, I had enough volcanology to, I had the pictures in the textbook of the pyroclastic flows and everything else. And this is not where we want to be. So that's when real fear took over, and we were running for our lives.
That picture that you showed, I think it was one of the later pictures. It was like, when I saw that picture, I said, oh my God, that's like a real life version of that last scene in Dante's Peak.
It was.
Truly, it really was.
Yeah, and that's what it felt like. And when I saw Dante's Peak, yeah, that's what, reliving that event.
Exactly. Thank you.
Kevin Cameron from SFU had a question.
That's incredible. I was just about to say, I was just about to type in that I had a question.
Yeah, there.
but I do. I was going to leave it till a little later. But being volcanologists, we all have that sense that, oh, just one more picture. It'll probably go the other way. So I was just wondering, personally, when was the point when you realized, okay, we have to get out of here, or we'll never make it out of here?
At the point where we're running back into the car. I mean, that was, as soon as we saw it coming down that east flank, it was, we need to get out of here. And there were many times, like as I was taking those pictures and we were actually enveloped by the cloud, we then, so there's a whole long sequence of events. It actually took several hours to get out. But yeah, there were many times during that period that I didn't think we were going to make it. But, and John Stix knows this because John and I have wandered around on active volcanoes together, is I am incredibly cautious. I am the most cautious of all of my colleagues. and I don't like to vacation around volcanoes which are not monitored. I check out the seismicity prior to any visits. Yeah, I'm kind of a chicken in terms of being around active volcanoes. And I guess, when you see something, and that was certainly not the biggest eruption that had been witnessed by any means, but when you see something of that magnitude, that incredible transformation of a landscape over a few minutes, I mean, it does change you. I mean, you feel something different, and one of them is fear.
Yeah, for sure. So thanks. You can ask another question later there, Kevin, as I come to you. I'm going to move back to Pierre Simon here, who had been bumped off and had to rejoin. So that's why he was strangely silent when I asked for him. So go ahead, Pierre Simon.
Yeah, sorry about these technical problems. Great presentation. I especially enjoyed the photos, which I had not seen, and the personal account, as I think that will be the case for most people. I was like, wow, okay, this is amazing. Might have to buy your book. Okay, my question is about the surges. In Jim Moore's paper, he talks about tal and so on, and then there's another paper later compiling all the surges, and they seem to be all phreatomagmatic, kind of related to Mars and wet eruptions in general. Are you saying that you think the blast at St. Helens was also phreatomagmatic?
Yes, it was, unquestionably. So there was juvenile material, like the cryptodome was basically disintegrated, a significant piece of it, and the whole edifice was essentially saturated because of it's a temperate volcano, a lot of snow and a lot of ice activity had started. So it started heating up back in March, and water was permeating downward. And so we had a saturated edifice. And when the pressure was taken off by the landslide, it became a phreatomagmatic blast. And I think one of the things, like further to, Kevin and John's question too, is that one of the channels of my career has been in hazard assessments. And one of the things I'm really adamant about is the ability of volcanologists to identify these phreatomagmatic explosions from typically magmatic, or even from simply phreatic explosions. And because each of them have a very different consequences on the hazard assessment of the volcano. So it's an important point. And all of our volcanoes are temperate volcanoes that have a lot of snow and ice, are susceptible to these kinds of phreatomagmatic eruptions under sort of similar circumstances.
Thank you.
Okay, well, thanks a lot, Pierre Simon. Pierre Simon helps out a lot with VIP, and just shout out there. Thanks for all that help over the years. Nadia had a question, and yeah, we have another question in the chat here. I'll get to it in a second there, Alan. Nadia, go ahead.
Hi, Catherine.
Hi.
Very nice seeing you, and thank you very much for sharing the very interesting pictures with us. So I have a question. I was wondering, was there like any attempt to measure the temperature of the pyroclast surges, or is it something possible at all to do it? I don't know about that.
Yeah, it's a great question. So the one of the things about a surge is it is cooler than a pyroclastic flow. And so at Mount St. Helens, because there was a lot of stuff, and by stuff I mean human stuff, so plastics, glasses, metals, paints, and the temperatures of basically the melting temperatures, particularly of plastics, is well known. So that they were able to take a look at what had melted and what hadn't from the blast, from the pyroclastic surge, and the temperatures were only about 350 degrees C. So that's cold relative to what you would have from a pyroclastic flow. And that is actually one of the key features. What we were looking at was actually a cooling, so and that's one of the keys about being phreatomagmatic. It was phreatic, and we were looking at steam and the sort of the maximum temperature of steam with a bit of magma thrown in there. But it was through melting of plastics that they were able to test the temperatures of both blast as well as the pyroclastic flows, which then followed within a few hours of that initial explosion.
Interesting, because like what I was thinking was like a temperature above 600 or something like that, but it seems it wasn't. Yeah.
No, so that's 600 and above is typical for pyroclastic flows. And that's what I said, that the particles are very different when you look at these kinds of deposits. They're actually quenched. So they get quenched by the steam. So they're not seeing magmatic temperatures sort of through their evolution. So you don't see there can be some vesiculation, but you don't see pumicles that you would see in a pyroclastic flow deposit. So the characteristics are quite different. You see fractures, you know, and also organics, depending on what the age is. You'll see huge amount of organics, just commutated bark and plants and whatnot mixed in with the deposits. So all of those are clues as to the kind of deposit that you're dealing with.
Okay, thank you.
Yeah, thanks, Nadia. Alan, you had a question, Alan Anderson? Just checking. Yeah, Alan, you unmute yourself.
Well, while we're waiting for Alan, did anybody guess what's behind me?
Oh yeah, I was going to ask actually. I really like the picture. How did you put it there? I don't think it's a real thing.
Oh, it is a real thing. But I'll tell you that. So this is the massive cave that could be the largest cave in Canada that I was part of the initial discovery. And the reason that I got involved was a volcanological reason. So this cave is it's in Wellsgrave Provincial Park here in British Columbia. And that's where I did my PhD. So I have had a long association with the park. I go back, well, basically on a yearly basis, you know, do naturalist talks, blah, blah. Anyway, the cave was discovered in now in April of 2 years ago, 2018. And it was discovered on a caribou survey. And they basically saw a big hole in the ground, and the helicopter pilot knew about me. He reached out and he said, "I think I found a big explosion pit." And you know, he told me where it was, and I said, "Well, I don't think that's an explosion. I don't think there's any volcanoes there, but you never know." And anyway, that started the process of discovery. We have not yet been in the cave, but hope to have the permits to do so. And obviously COVID has put a crimp in that plans, but hopefully we'll be trying to get into the cave in 2021. But it is in limestone in the Wells Gray area, and it's just, yeah, it's a fabulous site. If you can see it on Google Earth even.
Interesting.
So thanks, Alan. You're unmuted. So Alan's just typing in his thing, so he wants me to ask the question, I guess.
Yeah, I see it.
Yeah.
So yeah, sounds and smells. Another great question. So the sound. So obviously we heard nothing. And again, I don't know why we looked up, but you know, just scanning around in the morning and just we were eating breakfast. So we had no sound initially. Once the sound hit us, anybody who has stood at the end of a runway when a 747 lands, that's the kind of noise. It was overwhelming, punctuated by sharp cracks. And there's one point where I actually got out of the car. We were in the cloud. I'm looking up and I can't see anything, maybe see 20 feet in front of me. So the smell was kind of, you know, dirty ash, I guess is the only way to describe it. You know, sort of a dry, dusty kind of smell. And I'm standing there, I hear this giant crack, and I expect a huge block to come and land on my head. Didn't, but the sound outside the car was when we were close, was overwhelming, and from a distance it was just this constant roar.
So yeah, obviously Alan's saying thanks.
I see that.
Thanks for that explanation. I had the similar question about you know, some of the noises associated with a blast so big. I wanted to thank Catherine again for pulling together this 40th anniversary talk and highlighting that to everybody